In this series of Snap Circuits videos, we're going to look at project number 176, which is blowing off a doorbell, and finishing off with project 192 over here on this page, which is the video game engine sound. So, with project 176, blowing off a doorbell, there's our circuit in the book. There it is on our board. And the way this circuit is going to work is when we power it on, the music IC will produce an audio sound through our speaker, and it's going to be turned on by our two transistors here, our PNP and NPN. And our resistor here is going to constantly feed the NPN's gate so that the circuit stays on. Now, what we do with blowing it off is we're turning the circuit off momentarily, and we're doing that using our microphone and capacitor and resistor over here. So right now the circuit is going to stay on all the time. The music IC is just going to keep repeating and repeating. But once we induce current through our microphone, we charge up this capacitor here momentarily, and that diverts the current away from the transistor, causing our music IC to momentarily lose power, and the sound will cut out. Then once the capacitor is discharged, it will automatically restart and keep playing again. So with the aid of a straw, and I'm going to turn this circuit around so that I have better access to our microphone. Get my straw ready here. See, it plays normally right now. So it played normally there as we saw, or I should say heard, and then as I blew into the microphone using the straw, we heard the sound gets distorted and even cut out at times. So that's how project 176 is. Now 177 is a variation of it. So we're going to take our 6-volt lamp, put it in the place of our speaker, and we're going to perform the same experiment. So let me just change these connections out real quick. Take that. There. Let's see. Am I doing this right? Oh, that's because the 3-snap is in my hand. That's why I can't find it. And now, if we turn the circuit on, we get the same effect as we did, but now we've got the lamp being turned on by the music IC instead of the speaker. And again, if we use the straw, see, the effect is not as noticeable with the lamp, but it is still controlling it. So that's how 177 works. Now we're going to reconfigure this circuit for 178 and 179. So now we have project 178, which is blowing on a doorbell, and then we also got blow on a candle, which again is another variant of that project. And that's how it is in the book, and there it is on the board. And basically what we did is we took our 100,000 ohm resistor and moved it from the constant power up here down to the ground side. So what this is going to do now is when we power up the circuit, the music IC will come on and play one time and then stay off. And then when we blow into the microphone again, we induce a current through our capacitor here, and that will cause our transistor to turn on, which will then cause the music IC to turn on once again, and it will again play a song. And then it will shut off again until again we blow into the microphone and re-energize the circuit. So let's look at that. Let me move it around this way. So I will turn it on and it should play once. And you noticed as it was playing and then kind of died and went away. That's the effect of the capacitor charging up, which is taking the energy away from our capacitors here. So we're going to interrupt that with our microphone. So by blowing into the microphone, we are changing the current across that capacitor, allowing the transistor to activate and get the circuit working. Now, of course, we couldn't fully quite get it on. That's why it was sounding distorted. But that's how Project 178 works. Now, with 179, it's the same thing with our 6-volt lamp. So we're going to take our speaker out and replace it with our 6-volt lamp. There, and there, and this here. So when the circuit goes on, our lamp comes on, and should go out, which it did. And like with the speaker, you saw visually with the lamp there that the lamp kind of dimmed and then went out completely. And again, if we use our straw, we can keep the candle lit as long as we're blowing into the microphone. So that is Project 179 and 178, blowing on a doorbell, blowing on a candle. So now we're going to move on to Project 180, the Screaming Fan. So now we're going to look at project number 180, which is the Screaming Fan. And there it is in the book. And then we also got other projects from 181 to 184 that's going to change the capacitors and resistors around to make different effects. So there it is on our board. And the way the circuit is it makes use of our variable resistor because we're shunting power around between our motor and our speaker. And we're using our two transistors again, our PNP and NPN, along with two capacitors right now, our 0.1 microfarad and 470 microfarad. And the capacitance across these is going to affect the sound output and how the motor functions as we change where current flows with our variable resistor. So if we turn it on right now, with the way the variable resistor is set up, our fan is pretty much getting maximum power. As we shunt power down toward our speaker, see the fan is slowing down and the speaker's starting to emit noise. And if we go all the way to the bottom, so that's how project number 180 works. Again, we shunted power around with our variable resistor, and that changed the outputs between our motor and speaker there. And because of the motor's back EMF, we can hear the noise to the speaker, and the point to where it can actually squeal. So now, with project 181, we're going to change one of our capacitors around. So we're going to replace our 0.1 microfarad capacitor now with our 0.02 microfarad. So let me just snap that off. Snap this on. And now that's on. Now because this is a smaller capacitor with obviously less capacitance than the 0.1 microfarad, it's going to have the motor be able to start sooner, but also the whining is going to be higher in pitch and louder because there's less capacitance there for it to charge up. So turn the circuit on, and now we'll start ramping the resistor the other direction. Let's try discharging it. See how that behaved there? That's the difference with that capacitor. So that's project 181, the Whining Fan. Now we're going to do Light Whining. So now we're going to take the 100 ohm resistor out, and we're going to replace it with the photoresistor. So we get our photoresistor. Here's our 100 ohm resistor in the circuit. Let's just slide that out of the way. Put our photoresistor in, and now we're going to be able to vary the resistance at this point with the photoresistor by waving our hand across it. So then we start at the bottom there. Let me adjust this here. So you can see there in 182 with the light whining how the photoresistor changes the resistance there and affects how the motor operates and how the sound output changes, even with our changes on the resistance setting with our variable resistor. So we're going to move to project 183, and now we're going to change our capacitors again. But give you a moment for something else here. So for project 183, which is more light whining, we've gotten back to our 0.1 microfarad capacitor there across our variable resistor and NPN and speaker, but we've left our photoresistor in place. So let's start the circuit this time and see what difference we get. Now you can probably tell the frequency and the audio of the sound is lower pitch and lower in amplitude. In fact, there's so much there that all the way at the bottom. So we can see how putting back our higher capacitance capacitor there has made the tone lower and affected the circuit even more to points where it may not even work properly. So now with project 184, we're going to have a motor that won't start. And what we're going to do with that is we're now going to put a 10 microfarad capacitor here in place of this 0.1. So let me bring out the 10 microfarad. And we put our positive to the left, because that's where our positive power is coming from. Pull it off to the side here. And put this on. And the point is that there's going to be so much capacitor here that the motor's not going to be able to start up and get running. So let's see here. We've left our photoresistor there, so we still have photoresistor control. So we've got the resistor all the way at the bottom there, and it's clicking, and we see the motor is trying to turn here. Let me change our variable resistor a little bit. Again, even at all the way up, the motor isn't quite running. And our photoresistor is still affecting that output as well. So that's how Project 184 works, the motor that won't start. There's just so much capacitance here with this 10 microfarad capacitor that it's charging and discharging so much that we're not getting much constant audio or enough to really get the motor to continue turning. It's only kind of starting in little spits and spats, as you saw there. So we're going to move on now to Project 185, and that's the Whiner. So here we are with Project 185, the Whiner. There it is in the book, and there it is on the board. And here we're making use of our, again, two transistors, our PNP and NPN, with a couple resistors, our variable resistor, along with our whistle chip, green LED, and speaker. And what we're essentially doing here is producing sort of a tone generator. And by using our variable resistor, we'll be able to adjust the frequency of the tone that it generates. And then the following projects after, we're going to make use of capacitors here to alter the output of the tone. So when we turn our circuit on, and as you see it's producing a tone, you can sort of see that our LED is on there. If I move our variable resistor up, it goes up in tone, as you can tell. Move it about there, or to there, or all the way down, and now it's back to its lowest point. So we can play around with our frequency. And the thing about a frequency is that it's a whole bunch of peaks close together like that, and we're adjusting the distance between those peaks to kind of adjust how much frequency there is coming out, and so what the tone of the sound is. And even though it looks like our LED is on, it's actually flashing really, really fast. So we just can't perceive it with our human eye. Maybe the camera might have seen the flashing, I'm not sure. So with the next project, the lower pitch whiner, we're taking our 0.02 microfarad capacitor and we're placing it across our whistle chip. And now we're introducing capacitance into the circuit there. And as we've seen from the last project, adding capacitance to the circuit, especially in certain amounts, tends to make the tone lower because the capacitor is now inducing charge in it to charge the capacitor up. So if we turn it back on now the tone is lower and more drony. So that's Project 186, where we use our 0.02 microfarad. Now we're going up in capacitance to our 0.1 microfarad for the Project 187, which is the Hummer. So now you put this in there. We've now got even more capacitance in the circuit, so now it's going to probably sound even lower. See, now the pitch is lower. Those peaks, as I was talking about, are spread out even further. And so, again, it's lower pitch because of the added capacitance. Alright, so that is Project 187. Now Project 188 is an adjustable metronome, as they call it. And this time we're using our 10 microfarad capacitor, and this one is polarized, remember, so it's got a plus sign. So we need to make sure it's going to the right here because our positive power is coming down this way. So we don't want to put the capacitor on there reverse polarity, otherwise we're going to have a bit of an issue. So, as we just saw from the last two, every time we increase capacitance, the tone goes down, the frequency gets lower, produces a lower tone sound. So when we do this one, You can hear that the speaker's kind of pulsing. We see our light flash nice and bright, but it's not staying a constant tone like we had before. And by playing around with our variable resistor, see, we can make that faster now, just like we had before where we increased the tone with our other capacitors. By increasing our variable resistor, we can adjust how often that clicks, which is again why they call it a metronome, because we're charging up that capacitor, so it's kind of going bloop, bloop, bloop. So that's what it's doing there. And by using our variable capacitor, we can adjust how fast that capacitor is charging again by shunting how much current is getting to it. So that's project 188. Now the last variation of this project is 189, which is the quiet flasher. What we use for that one is we use our 2.5 volt lamp, and what we do is we take our speaker out. So let me disconnect the speaker here real quick. This might be a little tricky. Insert our lamp into there. Back in. Get everything back in there right. That right there. Take it off. Yeah. So now, instead of having the speaker, they call it a quiet flasher. So we're not going to have any audio output. We're just going to have our light turning on and off. So variable resistors all the way down. We're still using our 10 microfarad capacitor. And now when the circuit's on, you see that instead of hearing the pulse from our speaker, it's now pulsing the 2.5 volt lamp. And just like before, by adjusting our variable resistor, we can adjust how fast that pulses, again because of the capacitor there. Bring it down some. Bring it all the way to the bottom. So that's how project 189 works. Again, we just replace our speaker with our 2.5 volt lamp, and then that just pulses on and off with the circuit there. So the next one we're going to look at is project 190, which is the Hissing Foghorn. So here we are with project 190, the Hissing Foghorn. That's what it looks like in our book, and there it is on the board there. And this circuit again uses our two transistors, NPN and PNP, along with our variable resistor, but we've got our whistle chip and our speaker to help produce the output tones. And with this, we turn it on. It's not really doing anything right now, but as we move the variable resistor toward our whistle chip, see, we get kind of a scratching sound, which when I tested this, I found a little interesting because it's almost like a DJ scratching the record, as you see them do. But once we get to our halfway point and continue from there, now we start getting tones. So there's maximum there. And now we're at the cutoff point. So that's project 190. Now 191 is the hissing and clicking. And what we do there is we replace our 100,000 ohm resistor with our photoresistor. So that we take this out, put our photoresistor in its place. We got our variable resistor all the way up here. Then what we're going to do is move this to where we hear sounds, and then we're going to mess around with the light input on our photoresistor to see how that affects it. See, it sounds a bit higher pitched already. See, by covering it, we can kind of make it to a fast clicking sound, and then it goes to a tone when we vary our hand over it. So that's how the hissing and clicking sound Project 191 works for their photoresistor. Now for 192, it's the video game engine sound, and for that, we just remove those connections in the photoresistor, because now we're just going to make use of our fingers. And we're basically going to touch between A4, which is here, and then B2, which should be... Let's see, I think there might be a typo there. I actually need to turn my circuit on, don't I? Yeah. They meant C2, not B2. B2 would be right here. This is A4. So C2 is what you want, not B2. So they call this the video game engine sound. Now by varying my fingers on here, I can adjust how that is. So that's how Project 192 works, and the reason that that works is when I put my fingers here, I'm actually using my own body as a capacitor, creating a connection between the positive here of our battery and the positive input of our transistor, turning that on somewhat, and then we adjust again how much more additional current it gets by shunting it around with our variable resistor there, again diverting the current away through our whistle chip. So that is Project 192, and that completes this video.